rest of Module 10. We have learned all about light, how light moves, how light bends. We learned last week about the law of reflection. The law of reflection said that when light hits a surface, it does what when it comes off of it? It bounces back at what angle? The exact same angle of what it went to in the first place. So we had law of reflection. We had law of refraction, right? Refraction, we talked about that. When we say refraction, it's the same as a fracture, which means it actually breaks the path, so it's bending it. And when it goes from something that's faster into something that's slower, it bends in a certain pattern. It bends toward this line that is perpendicular to the surface that it's hitting, okay? So it's going to slow down, and it had a smaller slope. It's going to have a lower slope there, right? And if it goes from something that's slow to something that's fast, my little dotted line is where it would keep going if it was straight. When it's sped up, it bends away from the line. And so one of the things that was noticed last week, I think by Nathan, was that if you go fast, slow, fast, back into the same mediums, your initial path and your resulting path are going to be parallel lines. Because the same bend and fracture that you had initially is going to be you're going to have the inverse of it going backwards. Okay? So, knowing all of these rules about light helps us when we start making lenses. And I obviously wear glasses. I am nearsighted. So my lenses are convex lenses. And then, concave lenses. And if you're farsighted, your lenses would be convex lenses. And they do different things. And so just to go over that, a converging lens means if you're going to converge, if you're driving and you merge, right, you're converging all into one, you're taking lots of different lanes and you're making them come into one point. So when we have a converging lens, we have lots of light rays that are coming in. They're all getting broken every time they move in and out of this lens. And they're going to converge on one single point on the outside. Okay? If we have a diverging lens, looks like this, it's going to take all of your light rays that are coming in, and when they get bent and bent again, they are going to spread out. They are going to diverge. So same as if you're thinking about traffic. We're converging into one lane, or we're diverging, or diversifying. That's also where that comes from. So it's going to diversify and go out. And the neat thing about this is that our human eye does this already. God has created the lens of our human eye to change shapes in order to focus on our retina, on the back of our eye. Do you see my... Okay. And sometimes the lens in our eye doesn't work the best, or the elasticity gets changed and it's not focusing correctly. And so you go to an eye doctor and they give you glasses, and it's an extra lens to help your internal lens. And the whole point is to take the light that is being reflected off of every surface, and so it's coming back to your eye, it's hitting your lenses, and your brain is converging that into a focal point so that it can be clear. Okay? So you learned that we have a couple of different parts of our eye. We've got the cornea, which is the very front part of it. You can scratch your cornea. If you have something that goes across or gets sand in your eye, get an irritation with that. We've got the iris. And the iris is the black part, and it expands and contracts. Anyone ever been checked for concussion? Hit your head hard enough, they're going to shine a light in your eyes for concussion. Okay? The reason they shine a light in your eyes is that when you have a bright light pass over your iris and your pupil area, it will shrink and it will expand. So when it has a bright light, your brain says, way too much light. Whoa, that's too bright. I want to protect all the rods and cones in my eyes. So it'll shrink down. If you have a concussion, your brain is not sending those signals for it to shrink down, and the black part will not move in that, okay? So it says your pupil is the dark opening there. So we've got our iris, the colored and our black hole part, they work together, they shrink and they expand together. Our retina is the very back part of our eye. It's the movie screen, is what I like to call it. You can have, which is why as you get older, if you have a detached retina, it's a big problem. Because it is our movie screen on which everything is reflected and where all of the images converge, and where our brain has all of our signals of our cones and our rods so that we can take in information for it. And then the ciliary muscle is the one that just expands and contracts and moves your eye around. So often you will say, like if you've read or if you're reading late at night and your eyes get tired, it's sometimes we forget about the fact that our eye is a muscle. And every time that we're looking at something, that muscle is working. So if you had a weight in your hand and every time you wanted to move, you have to move that weight, you would be very aware at the end of the day that your biceps are tired, correct? But we don't notice it because our eye is just those small little movements all the time. But every time you focus, your eye is expanding, contracting, it's adjusting the lens. And so it's a very true statement to say at the end of the day, my eyes are tired. They really are tired. Your muscles are getting worn out. That's why things with our eyes can also cause us to have headaches. We can have eye strain. So the last time I had my glasses, got new glasses, there's a focal point on our lenses, and that's one of the experiments that you can get to try out today, is trying to find the focal point of different lenses. And so when we have a lens, how it is shaped determines where the light comes in, and it determines where everything is focused. When we have a diverging one and it's spreading out, where the light comes in, affects where it's thinnest, this whole curvature matters because it's going to change where it breaks on the outside. So if your curvature is off, or the focal, they call it the foci, focal point is off, then the light's going in a different direction. They had my focal point off by about 2 millimeters, a little high. So when I put on my glasses, I got sick almost immediately. I was really dizzy, my eyes hurt, I had a headache, and my brain was saying, this is not right, something is wrong. And so that's so neat how our eyes are a muscle and how God has adjusted all of the focal points and allowed us to work on that together. So one thing that our eye does is it absorbs color. And light and pigment work differently together. So you read that light is an additive color, which is interesting for us since we are all very familiar with paint. I know that your mom is an artist, and you guys know that I'm an artist, and everyone, when you're in kindergarten, learns that red plus blue equals purple. Awesome. And so we can mix colors, and so when we think of light, we think automatically, oh, well, I must need to just mix those colors, and I will get new colors of light. That is not how light and pigment work together, okay? I'm gonna go back to that. Okay, so with light, we have red, which we always expect red, right? Red, green, and blue. So what's the color that's off from the ones that we're used to when we talk about primary colors? Green. We've got green instead of yellow. And so when we talk about pigment primary colors, we've got red, yellow, blue. We can mix those to get all of the other colors in the rainbow. When we have light, we have red, green, and blue. And the more that we add them together, the closer we get to white. And so these are additive colors. When we're adding extra colors in, we're going to get to white. If we take out a color, then we can't have white. So if you have damage to your eyes, and one of those cone cells that we have, where we have red cells, green cells, and blue cells, if one of them is not working, you will no longer see white, because you have to have all three in order to see white. Are any of the boys in here colorblind? I ask boys because it is significantly more prevalent in men than it is in women. Okay, so people who are colorblind, my grandpa's colorblind. And so when you're colorblind, they call it color blindness. You're not really blind, as in you can't see something. It's that one of those sets of cone cells, either the red ones, the green ones, or the blue ones, are not responding properly to the light that is being taken in by your eyes. Your brain is not recognizing it as the correct color that it needs to be. And so therefore, you don't get the colors you're supposed to get. They're not adding up to the right amounts, okay? So TV and computer screens are produced using RGB. So now you know what RGB stands for. Red, green, blue, right? If you send information, so this is something that I'm very familiar with since I paint, and then I also digitize my art and I send it to a printer. If I am making a phone lock screen and doing it in a JPEG, I'm going to do it with RGB, because where is that image going to be housed? On a phone or on a computer. So it is going to be transmitted to me using light. So I'm going to use RGB to get the proper colors. But if I send it to a printer and they're going to use ink, they're going to use CMYK, cyan, yellow, magenta, and I don't know what the K is for, but it's a cyan, CMY, so cyan, magenta, yellow. And then I think the K is just like for the definition of it. So that's why we have some differences. And if you get involved in doing any digital design or graphic design, or if you go into like 3D printing or things like that, you'll see that you can save things in different formats. And so if you don't know what the format is, you might just say, oh, this sounds good. This is fine. But if you understand that RGB means this is involving colors using light, if you have a projector, if you have a digital, if you're doing it for a digital media, you're going to want to use the RGB. If you're doing actual ink, where it's actually printed, you're going to want to have it in CMYK. So that's good information for you guys to have for that. Okay, what is interesting? I brought these socks, okay, because we're going to combine the fact that these socks are pigmented with ink, meaning it is a subtractive color. Okay, our subtractive colors, which are our ink colors, absorb everything except what you're showing. So what you don't see is that as white light is going in here, that you actually have it sucking in all of the green and the blue light. And it is reflecting back to you the red light. The white ones here are reflecting back everything, right? Because light is initially all white. So if it's all reflected back, we see white. For something that's black, if light is initially all white, it's not reflecting back anything. So it's absorbing all of it. So our primary colors, for our additive colors of light and our subtractive colors of pigment work together. We have to think that out here in space, we have red, green, and blue going. We have in a pigment something, we have absorption of this light and it's reflecting back to show it. So I'm going to show you how neat, how neat it works. We've got a tool, I've got a light thing. I'm going to hit the lights here. What are those from? Are those outside? Let's see. Okay. So this is a light meter. We have our blue light. You want to see our blue light on here? Our green and our red. Okay? You guys can get up if you want, if you can't see. When I shine all of them together, it's, what's the color on the outside? White. It's white, okay? So when I use the socks and I shine the white light on it, what color are the stripes? White. Everyone see? White and red, right? They look like I showed you beforehand. We'll see if it works since I have this other one. Okay. Now, we know that the red stripes in this sock are reflecting red light. Okay? So what happens if I take away the red light and I only shine blue and green light on it? What color are the stripes now? You see that? So we know that they were red, but now they look black. Isn't that crazy? We can turn this on. Okay. That's a fun, you're like, oh my gosh, it's black. They turned black. They didn't turn black because we changed the color. They turned black because there was no light that they could reflect on it. And so since there were no red light waves for it to reflect back, it just absorbed everything. And we know that when it absorbs everything, it turns black. Okay. Let's see. So we're going to get, did anyone have any other questions? That's pretty much it with the different colors that we have. We're gonna do our 10.4 lab, and then I want you guys to have time to work together. After we do our lab, I do want to do the refraction one with everybody together, and then I'll let you guys kind of spread out and experiment as you would like. I'm just gonna do this up here.
Okay, so 10.4 has to do with the colors that your eye are taking in. So